welcome everyone to this first session of the workshop on rare event simulation and simulation of networks. And our first speaker is Jose Blanchet, who is here. Please, Jose.
Well, thanks for the introduction, and it's a privilege to be. Thanks very much to everyone for coming, and it's a privilege to be the first speaker of this workshop. And so this. There you go. I was saying so. Yeah, so it's my privilege to be here, like speaking as in the first talk. This workshop. So, as Soren probably mentioned, I don't know. As you realize, this is part of a wider activity, not only on rare event simulation, but on the simulation for a stochastic network. So I basically have a talk that centers around rare event simulation for stochastic networks, but is divided in three parts. So I will convey to you like three types of messages. The first one, which is color-coded yellow, although you cannot probably see very well because they look like both green, is like a general is a general message for the broader audience, in which I'm going to tell you what is the theme of this type of research, and the theme of that is common to of the research agenda of much people in the rare event simulation community. In the second part of the talk, I'm going to talk about I'm going to introduce for the general audience two types of algorithms that are the most common that are used in rare event simulation for stochastic networks. So that's one part of the message that I'm going to convey, but for the people who work on rare event simulation, I'm going to also tell you new results that shed light in the differences between importance sampling and splitting type methods. And that's the second part of the talk. And the last part of the talk I'm going to introduce a new class of algorithms that have superior performance compared to these previous other algorithms. And so kind of like a center to start the talk in going into these three topics. To center the conversation, I'm going to I'm going to borrow a sentence from a citation of Barad and Sabel Price. So the citation is large, it's like 2 pages, but one part of the citation talks about large deviation theory and how it has greatly expanded our ability to use computers to simulate and analyze occurrence of rare events. So that's a good thing, and that basically centers what is this topic about and what is going to be the research that you're going to be seeing throughout the course of the workshop, is in the ability to actually understand how to transform large deviations theory into optimal algorithms. And if you see this sentence, it sort of like conveys the idea of, okay, so if you take the large deviation theory as has been developed classically, that gives you a way to simulate rare events. But it's not really. In fact, in the first part of the talk, I'm going to talk about, in perspective, how are we where we are? Basically, why is it not exactly like that? So there is much work of people, basically virtually everyone who is in the audience, and especially in the later years, in the recent years of work of Paul and Hui, that has been particularly useful to actually understand exactly how do you actually use this theory into design of good algorithms. So I'm going to what do we mean by good typically? So we understand a good algorithm is an algorithm that satisfies some optimality criterion. In the context of that I'm going to discuss, so we have typically a probability that decreases exponentially to 0 at some rate. And the classical sort of concept of optimality that people aim at or look at in an algorithm is a concept of optimality that says that Well, the name of the game is design an estimator that you can implement in a computer that has the property that the second moment roughly is comparable to the square of the first moment, up to an exponential, sort of matching the exponential rate of decay. So as an asymptotically optimal algorithm is an algorithm that has has a variance that decays, the second moment decays like the square of the first moment, up to terms that are little of n in the exponent. So that is the most common concept of optimality. Also is called weak optimality. You still can get a situation where the second order is still exponential in n, but it's not with a smaller power. That's still acceptable. The algorithm is still optimal. Okay. In this sense, there are stronger concepts of optimality, a strong optimality, polynomial, and so forth. But I'm not. But this is basically the most popular one, and you sort of get the idea where are we going. So what does it imply? It implies that if you want to estimate a quantity that is small with epsilon relative error, with confidence at least 1 minus delta, then using replications, using Chebyshev's inequality, you see that the number of replications scales like a polynomial in 1 over epsilon, 1 over delta, and this part that I'm calling like complexity in some sense. Com is for complexity in terms of number of replications. So an algorithm is asymptotically optimal if basically it takes sub-exponential complexity in n. Now, of course, the total complexity is the work normalized complexity is basically scales like this complexity in terms of number of replication times the cost per replication. I think I should be using this. Yeah. Times the cost per replication. That's also going to be considered. So let me start with a classical example. So this example is an example that is cited many times in this end of a RESIM simulation. It's an example that was discussed in a paper, classical paper now by Parekh and Valran in the 1980s. And it's an example that I'm going to be discussing over and over throughout my talk. So I'm going to discuss the model in a fair amount of detail now. So I consider a two-tandem network. So when I think of a tandem network, this is exponential interarrival times with rate lambda, and I encode it in this form. Lambda is the arrival time, mu1 is the service time of the first network, the service rate of the first network, and the mu2 is the service rate of the second network. And I'm going to assume that the traffic intensity is a number between 0 and 1. What is the traffic intensity? The traffic intensity is nothing but the proportion of time the system is busy. That's the steady state proportion of time, not the station is busy. So this is the picture like that, right? So this is going to be the loyal companion toward the talk, this system, okay? So this is a continuous time Markov chain. I'm going to be talking about the embedded discrete time Markov chain. I'm going to use x1 of k to denote the number of people in station 1 at the k transition, x2 of k, the number of people in station 2 at the k transition. And so I'm going to use this assumption so that I can just directly talk of lambdas in terms of probabilities. This is without loss of generality up to scaling. So the state description of the chain looks like that. Okay, so this is where the chain lives. So on the x-axis, the number of people in the system in the first queue, number of people in the system in the second queue, and it transitions according to this arrow. So this describes the transition matrix. Okay, this turns out to be like that. So you have this dummy movement at the boundaries, and this is exactly what it is. Later on, I will be drawing pictures about the most likely paths, and this is what I'm going to be having in mind. Okay. And later on, I will be talking about the transition matrix. I'm going to denote it by k. This is, I hope it is clear what I'm saying, right? So the probability going from here to here is 0. And so this means an arrival to the first queue. This is a departure from the second queue, and this is a departure from the first queue to the second queue. That's why it's increasing. Okay. So in this example that I was that one of these examples in the paper of Parekh and Valran, you can use large deviations theory to conclude that the most likely path in fluid scale looks like that of a system that has So the question that I have in mind, sorry, is the probability. I say that the probability, here it is, the probability that the total population reaches level n inside a VC period. So starting from 0, the chance that you reach n before you actually go back to 0. So that's a small probability. And turns out that large deviations theory tells you that the most likely path in fluid scale looks like that of a system with these characteristics. So if the traffic intensity, the server that is the slowest server is the second server, then it's most likely that you are going to reach n individuals because you actually, you have a lot of congestion in the second server, which is the less efficient one. So it's very intuitive, it's gonna go like that. And you can, I'm not gonna tell you how do you do it, but this is something that the message I want to convey is that if you just take a look at what is the most likely path, you look at what large deviations theory tells you, it turns out to be this path. And so it would make sense to use a sampling algorithm that actually induces paths according to this Markov chain, and then weight according to the likelihood ratio, and use that as your estimator. So you are speeding up the computations by using what large deviation tells you is the most likely way, is the conditional distribution in fluid scale. Well, when you do that thing, you have an associated Markov chain K tilde according to the transition diagram corresponding to what I just described, but with this tandem system. And then you have your original transition kernel, and the importance sampling estimator just means at every stage you simulate according to this new system, this artificial system, and you have this odds ratio for each transition. This is the total likelihood ratio, and that would be your estimator. That's the natural estimator. Well, it turns out that you stop it as the first time you actually have n people. And what happens is that this number is actually very close to the probability of interest as long as you travel in the most likely trajectory, in the red gradient that I've shown in my previous picture. But if you deviate from that gradient, this number could be huge. And it turns out that that's exactly what happens. In a paper of Paul Glasserman and Steve Koo, and also a paper of Glasserman and Wang, 1997, they show that this sampler is not only not efficient, but actually by combining the parameters correctly can give infinite variance. So the message of this first part of the talk is well, the reason is because, of course, if you deviate from the most likely path, the likelihood ratio, large deviation theory doesn't tell you anything about how to protect the likelihood ratio for those paths. Those paths have very small probability, that's true. But if the likelihood ratio is big, then the whole contribution of the variance is going to be huge. So the bottom line of this first part is, okay, what is this talk about? What do these relevant simulation folks do? At least some of the research agenda is how to actually use large deviation theory to actually speed up optimally algorithms. And yes, large deviation is very helpful, but not directly. You actually need to think a little bit more. Okay. So now, in the process of actually thinking how to do it, then I'm going to tell you about. I'm going to move on and describe to you the first class of algorithms that are commonly used in relevant simulation. These are importance sampling algorithms. Importance sampling and splitting or particle type methods. Okay. Importance sampling. So for the problem of the tandem networks that I'm describing here, the first algorithm that was proven to be asymptotically optimal for arbitrary range of parameters, any parameters for tandem networks, is this by Paul Dupuy, Devin Caesar, and Hui Wang. So they do it for this total population and individual overflows in the network. And so there is another paper, a recent paper by Paul and Hui, that also show how to construct asymptotically optimal algorithms for any overflow event in any open Jackson network. I'm going to be talking about roughly what is the idea behind the construction of this one, because it's kind of the most intuitive one. This one, I will be stating a theorem that refers to this algorithm, right? But this is going to be like the message for kind of more precise message for like people that are working on these types of algorithms directly. Okay, so what I must note is that these two papers what they guarantee is complexity of this form, sub-exponential. So you still could have n to the power a half. And this is important because there are subtleties in the way in which these algorithms are constructed that when actually you go and analyze more precisely what is the complexity, it tells you a lot more insight into how to choose the parameters and what is the role that the various elements of the algorithms play in making the algorithm actually be efficient. And also I mentioned this thing because at the end, the later part of the talk, I'm going to describe an algorithm that has the best possible performance, so linear complexity. So it's basically the optimal possible performance. But to tell you, I'll tell you what is the idea behind this type of algorithm. Okay, so this is going to be like in a simple picture goes like follows. First, I told you that the importance sampling, this idea of using the most likely path directly, can actually give infinite variance. And the reason is that, well, yes, this is the most likely path, but if you do not protect the likelihood ratio, you could also reach this boundary, which is the total population equal to n, at this point, for instance. And then the most likely path, if you condition the process to actually reach the boundary at this point, doesn't look like that, of course. In fact, turns out to look like something like this. So goes from some time in this direction x1, and then goes up like that. Now, if you condition a point like that here, then it goes like this. And if you condition a point here, then it goes like that, right? So the idea, but what is an important observation is that, in fact, if you condition at a point here, or the gradient inside in the interior of this region is always the same. The gradient in the interior is always the same. So the gradient on the boundaries is also always the same, and the gradient here is also always the same. So in some sense, the right thing to do is to follow any one of these gradients, right? And you have finitely many of them, which I will tell you how to characterize later in the talk. So the idea is, well, why don't we take a mixture of this? Well, if you do a mixture of this, well, actually, if you do the most naive mixture, which is just at the beginning of the algorithm, just randomize and pick one, that is not going to work. So what turns out happen? Oh, so to each of these gradients correspond a system. Just as I said, like for this one, there is a system which is this tandem Q. For this one, there is a system which is this other tandem Q. So for each gradient, you can actually backtrack what is the system that corresponds to that thing. So the idea is that, well, if I know where is my trajectory, then I actually follow and simulate according to that system. So the idea is that, okay, so I'm going to randomize, that's the basic idea of the algorithm. I'm going to randomize, depending on my position, which system I simulate from the next transition, either this tandem network, either this one or this one, okay? And how do you randomize? Well, a very intuitive idea of how to randomize is, well, at this point, compute the probability that that specific gradient is the correct gradient. That is to say, what's the conditional probability that I exit at the particular point that corresponds to the gradient that is the most likely path, conditional on my current position. And that's basically the idea. So for instance, the weights turns out to take like an exponential form like that. And this reflects the conditional probability that you exit in that particular point given your current position. Now, it turns out that all these parameters are computed according to the fluid path. And sometimes in the algorithm, you can go off track the fluid path. But the remarkable thing to me is that the contribution is that there is a criterion that is a sub-solutions criterion that Paul and Hui used to actually show that this is the right thing to do. Okay, so for instance, if you are here, this would be corresponding to the conditional probability of exiting in this point, given that your current position is this. And this is correct for this path. But if you are here, in fact, you actually use the same weight. The same weight, like you just replace y by your position. If your position was here, is the same weight. So that's the remarkable thing, that the thing sort of self-corrects even if you are sort of doing something that you're not supposed to be doing. Okay, so what is the main message I want to say? So main message here is that important sampling, so you have this class of arguments that important sampling, you need protection. You need to protect for the possibility that you actually hit the target set from a different region, and the protection involves these mixtures and this state-dependent reweighting, okay? Something I didn't tell you is the proof technique. So the proof technique involves the subsolution of a differential equation to actually prove that this actually works. So now this is the message for people more like working on this. The result that I'm showing here is a paper with Peter Lin and Kevin Leder, where what we prove is that we take this paper of this algorithm of Dupuy, Cesar, and Wang, and this algorithm there are two ways of constructing these algorithms. You start from the original point, several, but the most common, start from the 0 and to the target set, or you start from the target set and you construct the algorithm very well designed for the target set. And this is that algorithm. So it's a more sophisticated algorithm, but for the total population of a tandem network. Okay. So what this algorithm shows is, what this result shows is that, in fact, it's not only sub-exponential complexity, but the complexity is bounded by a polynomial that involves basically the number of stations in the network minus the number of bottlenecks. So beta is the number of bottlenecks. Bottlenecks means the number of stations in the network that reach the maximum traffic intensity. So the maximum of the row i's is like the cardinality of the arc max of the traffic intensities. So what is peculiar is that it basically says, well, this algorithm, if you have a lot of bottlenecks, this algorithm tends to perform, well, the bound tells you, it's not a sharp bound. It actually becomes sharper as the number of bounds, the number of traffic, the bottlenecks increases. So, but it tells you if you have a lot of bottlenecks, this is actually a good thing. And the reason it's a good thing is because you actually, if you have a lot of bottlenecks, means you have a lot of possible ways in which you can reach the boundary. So you need to protect your likelihood ratio for more adversarial paths. And this type of algorithms, what they do is they are constructed in such a way that you have these mixtures that protect the algorithm. So this is why it turns out to be working like that. What we do is we translate the subsolution. It's basically take the subsolution approach and make it into a Lyapunov bound. So for folks who do Foster-Lyapunov criterion for MCMC, Jeff and Garrett, I think this is something that you could find interesting. Like there is also Lyapunov and drift conditions in these types of algorithms. So we use that approach. And what is interesting is that you see in the Lyapunov bounds, you see that the more gradients you actually have, the more protection, the more powers you need to add here. So it's important to actually try to get not as many gradients. And so this is important. So D minus beta. So keep in mind this thing, because this is kind of like an important thing. So I'm going to write here important sampling order n2 D minus beta plus 1. Okay? Then I'm going to come back. So now let me move on to the other types of algorithms. So this is in this. Yes.
Does the algorithm performance also improve with increasing beta, or it's just a bound that you have?
This is a bound.
So performance need not improve with increasing beta.
Yeah, I mean, no, this is just a sufficient condition. Yes. So now I'm going to talk about another type, the other class of animals in the zoo, right? So important sampling, particle methods. Okay. So these particle methods for, again, Jackson networks. So the idea is the following. I'm going to describe the algorithm I'm going to describe is the standard splitting algorithm. It's not, there is like a variation that is the most popular. Restart was introduced in this context of Jackson networks by Jose and Manuel Villena Altamirano. I'm going to talk about the standard version. So the standard version goes like follows. So you have this, you divide the state space in kind of like milestone events. This picture is kind of misleading because this picture shows this line is x1 plus x2 equal to n. So it suggests that the milestone events are spaced order n steps away. That's misleading. It's actually, they turn out to be space order 1 steps away. Because the idea is that you are going to have these milestone events created in such a way that it's not rare to transition from one milestone event to another milestone event, and you keep, going forward like that. So for instance, if you start from the first transition, you start at 0, so you start with one particle at 0, then you move the particle according to the original dynamics of the tandem network, nothing important sampling, just the same dynamics, and you move, say, to this point here. So at this point, you replace that particle, say, for 2 copies. Could be for r copies, but keep it simple, r equal 2. And now you reweight each copy by a half. Okay? So at that point, you advance each of these particles independently to the next milestone event. It goes like that. Say, for instance, this one reached this milestone event here, the other one here. These are independent transitions. And you again replace these 2 by 2 copies, but now each has weight equal to 1/4. Okay? That's very easy. So then the next one, I'll tell you how to kill particles. You get kill particles. So here, for instance, this one reached the next milestone event like that with a red here. This one took like a very long detour here, reached like many milestone events down, but somehow it sort of like makes it right and comes back and hits the next milestone event up. The restart method would say, well, kill them, because it doesn't make sense to go down. This is most likely is going to die. But this is the method that I'm going to discuss for which the results are done, is for this method where you just kill them. If they go back to 0, if they go to the next level, you just keep them. Okay? So for this one died here. So kill this particle, and then you have these other particles, each of weight equal to 1/8. Split them in 2, and then continue. Okay? That's the algorithm. All right. So now let's say I want to compute the probability starting from a point x that you reach total population equal to n before you come back to 0. And I'm going to tell you quickly, okay, how do you actually, the trick here is how do you space the milestone events? How do you actually do that thing? Okay. So here's a heuristic, very quick way of seeing how to do that thing. Oh, by the way, so I just need to say, what is the replication? The estimator is the number of particles that make it to the last milestone event, so that make it that reach total population equal to n, divided by the weights. So I was picking r equal to 2. In general, it's r whatever, right? And L of nx is the number of levels that are required to actually reach n. Okay? So this is the only random thing is this n is the number of particles that make it. This is deterministic. It just depends on where do you start. Given the milestone events, this just tells you how many milestone events are required to reach n. Okay, so so this in the restart algorithm for these Jackson networks, the way how to space the milestone events was conjectured by Villena Altamirano and was proved more general than Jackson networks by Paul Dupuy and Tom Dean. But for Jackson networks, the story goes like follows. This is a very heuristic. This tells you exactly how to position the milestone events. The idea is that, of course, you don't want to end up in a situation where you have exponentially many particles, right? So what's the expected number of particles that you're going to have at the end? Well, you're going to have r to the power number of levels times the probability that you actually reach the end of the level. That's how the particles, that's the expected number of particles. And you want this to grow sub-exponentially in n. So if you have a bound of this form, which is what this sub-solution tells you, sub-solution because it's a lower bound on the rate, but that translates into an upper bound on the probability. If you have this upper bound, then you just take this logarithm here, and then this tells you that this ln x, this number of levels starting from position x, has to be set according to a linear function. So it's very easy. Once you have this linear function, this theta star is a parameter that comes from large deviations. Just compute that parameter, and you just divide up according to the level curves of this linear function, and this is how you should set up the milestone events. Just level curves of linear functions. That's it. Okay. So it turns out that this turns out to be have this property, and turns out to overall complexity of the algorithm turns out to be sub-exponential complexity. All right. The algorithm, the result that I want to show is this one, this refinement. So this is a paper with Kevin Leder and Yishi Shi. So if you take this scheme of Paul and Tom, now what turns out happens is that the total complexity is scales like a polynomial in the power of 2 times the number of bottlenecks plus 1. Okay, so I'm going to write here splitting okay. Now this in fact this is not sharp, but it's actually closest than the importance sampling. So this one is actually the gap in sharpness is actually closer than what the proof says for the other one. So this one actually tells it's a more sort of honest bound of what it really happens. Okay, so I'm not going to tell you what the proof is, but the proof boils down to actually understanding very well what's the conditional distribution of the position of the particles, given that they reach these milestone events. But what I want to concentrate on in terms of discussion is precisely this dependence on the traffic on the bottlenecks. So I've heard like in talks like saying, well, you shouldn't use when you actually have these big, relatively large size networks, if you use these restart methods, they tend to be more robust in terms of the variance performance, right? And this probably sort of sheds light into why that might be the case, because if I give you a network like that, with 10 stations, and it's a network that comes from some engineering design, most of the time this network will have only few stations that are bottleneck. And if you see, then it makes sense that if you have few stations that are bottleneck, then this complexity doesn't really get compromised too much. So that sort of gives an insight into why this probably is the case. All right, so let me summarize this second part of the talk. So the second part of the talk, I introduced the two types of more popular schemes: importance sampling and splitting, restart, related to restart. By the way, I should mention, I think the difference, if I haven't analyzed the restart because of, as I said, I assume that the particles get killed when they go to zero. Restart kills the particle level priors, but I think the difference will be just the power in the analysis. So just, you speed up, restart speeds up by a linear term at most. So these are the two key messages for in terms of the contributions for the simulation, these two key results. Now, one thing that I want you to keep in mind is that for these types of models, these Markovian models, you actually have another way of computing the probability. So this U of x is the probability you hit n, all population L before go back to zero starting from x. And by doing first transition analysis, you can set up a linear system with some boundary conditions with order n to the power d unknowns. The system is quite sparse, so you can actually solve the system in power less than n to the power 3 times d. So in principle, there is a benchmark that is sub-exponential. So when you actually run these algorithms, they run a lot much faster, and these bounds that I just said actually tell you that the complexity is more than n to the 3d, which is what would be solving the linear system by Gaussian elimination. So this sort of like justifies and tells you, if you have when you have less than half of the network are bottlenecks, you probably are better off using this, and if it's more than a half, well, the guarantee is that this is better. That's the guarantee. It doesn't mean it's sharp, but it's a performance guarantee. Okay, so then the next thing was, frankly, I was kind of interested in trying to prove a complexity that did not depend on the size of the network, like a power that didn't really reflect the size of the network. Because you see, the best thing to have is like a linear, if you could actually do the zero variance importance sampling, so the conditional distribution, it would involve just a path that has n elements in it, order n. So in principle, there is something that is linear. It's an ideal thing. Maybe it's not possible to get, but you know, that's kind of like the golden standard. So then I went and I thought about another idea. So this idea actually has been discussed many times. So this idea of actually looking at the time reverse process. In the last RESIM meeting, Victor sort of gave a talk about, you know, using importance sampling, restart, and sort of time reversal ideas. And so it's kind of it's unfortunate that Victor is not here, but today, because I think he probably would have liked that to see that in fact his intuition of doing time reversed is actually the right thing to do for these problems. You know, Sandeep and Victor worked on a paper in which they sort of think through the similar ideas that I'm going to describe. This time reversed represent ideas to understand the conditional distribution have been studied before in the paper of Paul, and we also those ideas are studied, and this old paper by Anantaram, Heidelberg, and Sukas as well. But so most of the time, this trying to understand what the conditional distribution of the Jackson network is in terms of the time reverse process has been used to actually simulate the process forward, not actually trying to get the process backwards. So I'm going to describe this the mechanics of this algorithm again in the context of tandem networks. So I use this notation x1, x2. The whole vector has d components, in this case 2 components, and the Markov transition kernel k satisfies this. It's the picture I showed at the very beginning of this talk. So Jackson networks have the property that you can compute what's the time reversed Markov chain. In fact, much more general networks allow these properties. Kelly networks there's a whole book by Frank Kelly that has useful models for which you can do this, for which you know the elements of the time reverse Markov chain. And what I'm going to discuss here, I believe it's applicable to all these models. Okay. So you start from this transition kernel, you compute this backwards kernel. And so, for instance, in the case of Jackson networks, if for people who are not very familiar with these queues, type of queuing problems, the time reversed Jackson tandem network is very easy to compute. It's just just reversed the flow in this direction. It's very easy. So that's the time reversed Markov process, turns out, and the steady state distribution turns out to be geometric. The steady state number in each of the stations is geometric, with mean equal to the traffic intensity divided by 1 minus the traffic intensity. So that's known. Okay. So for this Markov chain, we know how to compute this k in k time reversed k. All right. So basically, the whole idea of the algorithm comes from a very simple identity. In fact, it's just the following identity. If you compute the probability that you go from 0 to total population equal to n, more generally you can do for more general sets, but I'm for the sake of explaining this algorithm, I'm considering total population equal to n. You have the following representation. So if you actually do this calculation by hand, what do? Well, you add over all possible admissible paths. Admissible paths are paths that satisfy this property, and I'll show a picture in a minute. Tx is the first hitting time, T0 is the first return time to the origin, and Tn is the first hitting time to population n. So you start and you multiply these transition kernels for these paths. So you have a contribution for the beginning, x0 is equal to 0 in this case. Then you have a contribution of the products in the continuation region. So that is to say, before you hit either total population n or you come back to 0, and you haven't reached x, then you get to a point where you reach x, then you can reach x many times, and then at some point you hit n before coming back to 0. Okay? So the path looks like that. So you start from 0, you wander around, you go x, you wander around, you might go back to x again, you might go back to x again, and at some point you hit total population n, right? So this is how the paths look like. Well, if I multiply and divide by 1 over pi here, I recognize that this just becomes the time reverse kernel times pi x1. And I can do the same thing with the guy that is next. That will be a transition from x1 to x2, blah, blah, blah. All of them, I would obtain this representation here. So this kernel is representing transitions from x1, x0, xtn minus 1 to x. So this is a typo. This should be xtn. And there is a point where I cannot do the swap anymore. So I have this extra contribution of pi here, right? Now, if I rename the paths, now I just say, well, x0, my new x0 is x tau n, like this. Then I have this representation. And this representation in terms of expectations, I just think what does an admissible path means in the time reversed system. An admissible path would be a path that starts from the total population n and hits x. So it's the same picture that I showed before in terms of what you see. It will be the same path. So you must start from a point here. You must immediately leave this region. You cannot hit twice in the time reverse. You must immediately leave. You have to reach x at some point, and you have to go 0 before you actually come back to n. These are the pictures of the paths. So in terms of this, now I define what does that mean in terms of these first passage times for the backwards time reverse Markov chain. And it's just simply saying that, as I say, that now you have to hit 0 before you go back to n, and you have to hit x before you either hit n or 0. Those are the admissible paths. Now, an admissible starting position is a position for which that has the property that the probability of this event is positive. Of course, you cannot start from something that doesn't have that property. So, for instance, in the tandem network, if you have the system that goes, this is mu1, this is lambda, goes here mu2, and then you go in the backward system, right, mu2, mu1, and if you start according to some distribution that has the sum of these two components equal to n, if you have, for instance, n people here and 0 people here, that's how you start the system. The probability, that is not admissible. That's not admissible because it's impossible that you go from a situation where you have n people or more to a situation where you have less than n people. You must transition either here or you increase another one. So that wouldn't be an admissible starting point. Okay? So, but basically, what it says is that what I showed is the second equality here. This is what it says. So this probability is the same as computing this probability. Now this is starting from the steady state distribution, but conditional. This steady state distribution just comes from the fact that I could not cancel the last contribution of the pi, and going backwards. Now this second part is very easy. This first equality just comes from the strong Markov property. Once you reach x, then you can separate these two probabilities. So at the end, the probability you start from any point x, you hit n total population before you come back to 0 is this ratio. Now if x is of order 1, which is what I'm interested in, The denominator is something that is bounded away from 0, so can be estimated by Monte Carlo. That's not a rare event anymore. So the complexity of that estimation procedure is independent of n. So I'm going to concentrate only on the case x equals 0. So this probability would be equal to 1 because x is the first heating time. If I start from 0, this is 0. So now I'm interested, when I have this representation now, the representation says I can estimate this probability by first starting my initial position in the admissible points according to the steady-state distribution, and then simulate the time reverse process according to its original time reverse process, compute this expectation, and that's an estimator. Okay? There is an important sampling version of this estimator, but I'm not going to discuss that. This is conceptually is basically what the idea is. Now, let's say that I can estimate this probability with complexity that is order 1 in the uniform in n. So the probability that I pick a point at random from the steady-state distribution and has the property that the sum of the components is equal to n, and also I disallow this type of positions. Right? So I do not have zeros here that in the sort of stations that are admissing stations. This is admissing a station from the standpoint of the forward network. This is admitting customers. Well, if I can do that, and I can sample I can estimate this probability in order 1 time, and I can sample from that distribution in order 1 time, and I can simulate from the time reverse network in order 1 time, in order n time, you know. Now this is the whole path, given that I start from this position, admissible position back to 0 in order n times. So then the total running time of the algorithm is linear in time, linear in n. And that's basically what the algorithm does. So the idea is that this is a static problem. This x0 has components that are independent geometric random variables. And the most interesting part, well, that's interesting. Another interesting part is how to make sure that, in fact, the tandem network, time reverse tandem network, naturally will have probability bounded away from 0 of hitting going back to n. So in other words, any point in this initial configuration has this property that you are going to hit 0 before you come back to n with positive probability, uniformly bounded away from n. It doesn't matter how large n is, doesn't matter what is your initial position, this happens. And so the key steps in the proof I'm not going to say, but the idea is that, you see, I'm allowed to do whatever in the first k transition. So what I do is I start from this configuration that is admissible, and I just make sure that the system, that I move away from the boundary enough people. I just make a lot of people depart from the queue. That has a probability that is independent of n, that event. I'm after a lower bound, so I can intersect with whatever I want. I intersect with such a thing. And then I realize that, that this network the backward network is stable. So that means that the expected number of people that are going to leave is more than what is going to come in the network. So the drift is going to have negative drift, and then I use some Chernoff bound to make sure that after I remove these large enough customers, the chance that I go back to n is arbitrarily small, depending on k. So this can be estimated. This probability can be estimated in order 1 time uniformly in n. Sorry, order n time, because each path actually requires a vector sample path of size n. And so for the last part, the conditional steady-state distribution, I just realized that as I said, all what I need is to make sure that at least one of the receiving stations, so these stations, or if it's more generally a Jackson network, at least one of those stations that can receive traffic from the exterior, that receive migration customers, has at least one customer. And I know that a geometric random variable conditional on being larger than 1 is also a geometric random variable plus 1, right? So I can concentrate on something that is sum of geometrics equal to a large number minus a number that is independent of n. So it's an order 1 number given the architecture of the network. So this is how I do it. At this point in the talk, you can, if you think, okay, now the problem is very easy, you can do exponential tilting for this type of calculations, I would be satisfied. That's already something that is carried. You can use cross entropy if you want, for this part. You can do a lot of stuff, many algorithms for this probability, to estimate this probability. These are independent geometrics for this event. The one that I use, exponential tilting is good, but it's not going to give you order 1 complexity, by the way. I mean, it's going to scale, in fact, with the number of stations. The one that I use is a state-dependent sampling for this probability. So if you want more generally compute the sum of independent negative binomials, not IID, just independent negative binomials, this probability via Monte Carlo with a complexity that scales order 1 uniformly in n, I use a state-dependent sampler with mixtures of the following form, with some probability that I pick according to the sums that I have been observing. I simulate the negative binomial given that the next increment actually makes me reach the boundary, and the complement, I do something that is kind of funny. I mean, that works out like that. But basically, I do two things. Either I make it the next jump to reach, and I sort from heavier to lighter tail in terms of the index. And the other one, basically, what I do is I look at the level here. This is the number to reach, n minus s. S is the current sum that I have observed after simulating, say, k negative binomials. And basically, I have order 1. I need to put something that is order 1 distance from here. And from here to here is the conditional distribution. So I need to kind of move a little bit. So it's not exponential tilting. That's not going to give optimal sampler, but this family actually gives. So you do some sort of Lyapunov type argument for this part. Okay. But that's, so that's it. So the total contribution is that, yes, you can estimate, and in fact, you can simulate conditional paths given this type of events in order n complexity. So that's, basically as good as it gets. All right, so I'm going to finish with just a summary of what did I tell you in this talk. I told you first, set the stage of what is one of the, what constitutes an important part in the research program of this community, which is how to use these large deviations to construct optimal algorithms. I gave you a sense of what optimality means. Then I told you about two generic types of methods that this community uses for addressing these problems: importance sampling and splitting type methods. I told you roughly what is the idea behind the construction of these optimal algorithms and hinted about the methods. And then at the end, I told you for this class of problems, an algorithm that is basically exhibits optimal, in the strong sense, optimality complexity. That is what I say in this talk. And since I know that this talk is going to be online, so I also have these references of the papers that I mentioned here. Okay, this is it.
Thank you. Time for one or two brief questions or answers, people.
Do you want to say anything about the generalizations to non-exponential networks?
Yes. So, very good. What we understand very well is for this class of algorithms, let me tell you these things. Okay. For these types of algorithms, right? What we understand very well is these criterion, which are based on Lyapunov functions. Yes. So the Lyapunov functions require an underlying Markov process. You need to have a Markov structure to actually state a Lyapunov function. However, in principle, there is a natural algorithm that you can try to use for these more general networks. which is, you know, in principle you have the calculus of variations problem, even for generalized Jackson networks, that you could try to solve on the fly. Like at every point in time, you try to see what is the optimal change of measure. There is the methods that have been developed sort of hint on what is a good sort of strategy, but the techniques, in fact, these types of problems are still open for those things. Now, there are some, as you know, there are some things that you can do with networks that are not Markovian networks, especially in the many server queues for many server systems. Like we have this paper in which we compute large deviations probabilities for net loss queues with general service times, and you know, within a class of inter-arrival time. So this use in a way this type of time reverse idea. So there are like a lot of things to do in terms of actually proving the optimality, but there is already a fair amount of guidance in terms of how to do that. I mean, one thing that I was trying, but I frankly didn't do, like I didn't think too hard, is how to approximate the conditional distribution. There are papers by Bob Foley and by David McDonald. There is a paper by Musolier in 1999 that have these still Markovian networks, but the idea is to approximate, you use a system that for which you know how to compute the steady-state distribution and approximate, and basically use this type of time reverse idea. I frankly think this time reverse idea looks like I am using a lot of the system, Jackson, and I don't think so. I have used this idea more generally for, like, for instance, long-range dependence queues, like Gaussian queues. I use very similar type of idea, like bridge sampling, and for this many server systems. So, you know.
Well, thank you. I think we have to progress with the program, so let us say